You have also studied in your previous grades that rational numbers can have either a terminating decimal expansion or a non-terminating recurring decimal expansion. Here, we will consider a rational number, say p by q, such that q is not equal to 0, and explore exactly when does the decimal expansion become terminating, and when takes a form that is non-terminating, repeating, or recurring. The best way to go about doing that is with the help of examples. Let us observe the following rational numbers. Now, 0.675 is equal to 675 by 1000, that is 675 by 10 to the power 3. 0.312 is equal to 312 by 1000, that is 312 by 10 to the power 3. 0.2625 is equal to 2625 by 10,000, that is 2625 by 10 to the power 4. 11.6704 is equal to 1,16,704 by 10,000, that is 1,16,704 by 10 to the power 4. As expected, these can all be expressed as rationals with denominators expressed in powers of 10. Now let us explore by factorizing and cancelling all the common factors from the numerator and denominator and see what we get as result. 675 by 10 to the power 3 gets factorized as 3 cubed times 5 squared by 2 cubed times 5 cubed, that further simplifies to 3 cubed by 2 cubed times 5, that is 27 by 40. 312 by 10 to the power 3 gets factorized as 3 times 13 times 2 cubed by 2 cubed times 5 cubed, that further simplifies to 3 times 13 by 5 cubed, that is 39 by 125. 2625 by 10 to the power 4 gets factorized as 3 times 7 times 5 cubed by 2 to the power 4 times 5 to the power 4, that further simplifies to 3 times 7 by 2 to the power 4 times 5, that is 21 by 80. 1,16,704 by 10 to the power 4 gets factorized as 2 to the power 5 times 7 times 521 by 2 to the power 4 times 5 to the power 4, that further simplifies to 2 times 7 times 521 by 5 to the power 4, that is 7,294 by 625. But wait. Can you see a pattern developing? When we have converted a real number with a terminating decimal expansion into a rational number of the form p by q, where p and q are co-primes, the prime factorization of the denominator, that is, q, has a combination of either powers of only 2, or 5, or both. This happens because powers of 10 can only be factorized into powers of 2 and 5 as prime factors. This holds true not just for the handful of examples we have covered till now, but for all real numbers that have a terminating decimal expansion. Thus, we have learnt a very important theorem associated with terminating decimals, which can be summarized as follows. Given a rational number a, whose decimal expansion terminates, it can be expressed in the form p by q, where p and q are co-primes, and the prime factorization of q is of the form 2 to the power of n times 5 to the power of m, when n and m are non-negative integers. You must be thinking now, is this theorem true the other way round? When we go back to the same examples in the reverse manner, we will find that, yes, the reverse of the same theorem also holds true. Stated formally. Given a rational number a that is of the form p by q, where p and q are co-primes, and the prime factorization of q is of the form 2 to the power of n times 5 to the power of m, when n and m are non-negative integers, then the decimal expansion of a must be terminating. Now, through this theorem we have sorted out the terminating decimal expansions. It must be bothering you now, that do we have a theorem to identify when the decimal expansion goes non-terminating recurring? Once again, let us arrive at that identification through an example. Consider the rational number 3 by 7. Note that the denominator 7 is clearly not of the form 2 to the power n times 5 to the power m. By long division, you will see that remainders are 2, 6, 4, 5, 1, 3 and so on. Worth noticing is the fact that the remainder never becomes 0 even if we proceed further with division. Also, the remainders begin to repeat after a certain number of stages. This also causes the quotient to repeat in blocks of digits 4, 2, 8, 5, 7, 1. What we have witnessed here is not only true for 3 by 7, but can be extended to any rational number that does not have a denominator of the form 2 to the power n times 5 to the power m, that is, which does not follow the terminating decimal expansion theorem of rational numbers. For such numbers that have non-termination recurring or repeating decimal expansion, we have a theorem that states, given a rational number A that is of the form P by Q, where P and Q are co-primes, and the prime factorization of Q does not take the form 2 to the power of n times 5 to the power of m, when n and m are non-negative integers, then the decimal expansion of A must be non-terminating recurring or repeating. Therefore, from the discussion on these two theorems, we can safely conclude that the decimal expansion for every rational number can be either terminating or non-terminating repeating. Please pause the video, rewind and play again to absorb what has been covered in the topic. Let us proceed now.